Okay. So this review will be on light and quantum theory, which are sections 3.1 and 3.3 in the textbook, and it's lesson 5, lecture 5. In the modern atom, electrons are really, really, really small in comparison to the nucleus and the size of the atom. I don't know, you've heard of the example of in a football field, like electrons are so incredibly small, like not even comparable. And that light travels as a wave, and it oscillates in an electric field and in a magnetic field, which are the fields are perpendicular to each other. Waves are they have different terminology, so we'll go over the terminology. So as you can see here, in the curve, a wavelength is the distance between where a wave hits the same point. So like it's the difference between a crest and a crest, or a peak and a peak. And as you see here, a peak is the highest point in the wave. So a wavelength would be the distance between one peak and another, or the distance between one trough and the other. So the trough here is the lowest spot. So it's the same, no matter where you measure it from. Any 2 points in the, it has to be from the crest or the trough, because if you measure between any other points in the same area, that's not the whole wavelength. So between the crest or the trough is the wavelength. The amplitude is the height of the crest, or the height of the trough. It's half of the total distance from a crest to a trough. Not the entire length, so it's different from the wavelength in that aspect. The node is the 0 point, where the amplitude is 0. And yes, that's the node. Wavelength, as we described as the length between the two crests, is represented by this symbol, the Greek letter, and it's called a lambda. It's measured in meters because it's a length. Frequency, which is another term that isn't a physical aspect of the wave like all the other things that we've talked about, but is another aspect of the wave, is represented by this Greek letter nu, which looks like a V, but it's not. And it's the number of wavelengths that pass a point for a specific time interval. And its units are in hertz, which is 1/1 second, or sometimes it's described or written as a second to the power of -1. And it's the number of wavelengths that pass a point for a specific time. Frequency and wavelength are inversely proportional. Where I talked about it? I had it in the slide somewhere, but so I like to think of it as like just a line with dots on it, and the distance between two dots is the wavelength. And then if the distance between the dots is longer, that would mean a longer wavelength. If the distance between the dots is shorter, that would mean a shorter wavelength. And then if you have like a specific point, and then the line is moving across it, like the line is moving with all the dots on it, the number of wavelengths that cross that point, the number of points on the dot that cross this marker over a specific interval is the frequency. If that makes sense. So the wavelength is the distance between the dots on the on the line, and then how many dots on the line past the marker in a set amount of time, which is usually 1 second, is the frequency. It just helps me because it takes out the other dimensions, so it's easy for me to understand. Frequency and wavelength are inversely proportional. So the longer the wavelength, the longer the distance between the dots, the less dots cross the marker in a set amount of time, which means that frequency is lower. Frequency is how many wavelengths, how many of the dots cross the marker in a set amount of time. If the space between the dots is bigger, then there's less dots that can cross it, and so the frequency is lower. Electromagnetic spectrum speed. Oh, this is where I had think of lines. So all electromagnetic waves travel at the speed of light, which is 3 times 10 to the 8 meters per second. And you do have to memorize that number. It confused me a bit when I first learned about that, how they could all be traveling at the speed of light and be at such different frequencies, but all the lines are moving across at the same speed. It's just dependent on how big or far apart, how far or close apart the dots are. Visible light is just a very small portion of the electromagnetic spectrum. As you can see here, it ranges from about 400 nanometers to 700 nanometers. You do have to memorize that the order of the colors. So we talk about it a little bit later in this review, but the energy of the electromagnetic wave is proportional to the frequency. So a higher frequency means higher energy. And so the way that I remember this is, like, if you think about a candle flame, the orange or yellowish part is cooler, so you can like whip your finger through it even. But the blue part of the flame is really, really hot, so it's more dangerous to touch that. And that's kind of like counterintuitive to how like we use colors with like the red and blue faucets for hot and cold. But in reality, blue is hotter and red or orange is colder. So I remember the flame, and that helps me differentiate. So if you just remember Roy G. Biv, and then flip that, that's going from highest energy to lowest. Okay, so speed of light calculations. If a typical microwave operates at 2.45 gigahertz, how many wavelengths does it take for the wave to travel 61 centimeters? Go ahead and solve this with me. So I'm just going to do it on my own scratch paper, and you can do it on yours. So first we have to convert gigahertz to normal hertz. Actually, I don't think I have time in the review for this, so I'll just go ahead and give you the answer. So the wavelength is 12.2 centimeters, and then how many wavelengths does it take for the wave to travel 61 centimeters? It's 5 wavelengths. Blackbody radiation. So blackbody radiation is light emitted by a blackbody, and light doesn't necessarily mean visible light. It's anything on the electromagnetic wave spectrum. A blackbody is something that absorbs all frequencies of radiation. It's continuous in its absorption. At room temperature, it looks black, and this confused me, but it's not black. Dark doesn't, it has to be dark, but it doesn't necessarily mean that it's the color black. So like how the coils in a toaster, like here it's lit up, but in the coils of the toaster, they're not necessarily black, they're just metal. The color of, yeah, they're metal, gray or whatever. And then at high temperatures, it emits light or radiation. or like visible light. Continuous emission spectrum of blackbody radiation. So blackbody radiation, oh, I guess I was wrong here. Light emitted by a blackbody, it is visible light. So because even at low temperatures, a blackbody is always radiating electromagnetic waves. It's just at lower temperatures we can't perceive it because it's infrared. So like if you wore infrared goggles, you could see it, but the radiation that a black body emits, but normally you can't. So the continuous emission expression spectrum is proportional to temperature. So the higher the temperature, the higher the wavelength, which is how we get the point where we can, where it emits visible light. Scientists struggled with this because the theory clashed with the actuality. Theory says that the higher the frequency, the higher the energy should be. And that by the time that it gets to the ultraviolet region, it should be like, right, it should be there. Oh, sorry, you can't see it with my finger, but the higher the frequency, the higher the energy, and by the time you get to the ultraviolet region, black bodies should give off infinite energy, but that just doesn't happen. So Max Planck says that he said something, he came up with something different to that theory, which was clashing with actuality. He said that energy is proportional to frequency, and that objects absorb energy in quanta, so that it's quantized. You can see here, energy can only have certain values, not an infinite amount of values. Like, so relating that to an equation, energy equals n times h times frequency. So h is just Planck's constant, which is 6.626 times 10 to the negative 34th times joules times seconds. That's the unit, is joules times seconds. And you do have to memorize that number. For me, I just, this and then also the speed of light as well. I just like to, on the calculator, you can, I don't know if I have it, yeah. On the calculator, there's a certain button you can store it. If you have it just a scientific calculator, there's like A, B, C, D, E, F. You can see in like above the buttons, and you can store numbers in there. So like during the test, you can just use that. And for me, I just Googled my type of calculator and then figured it out like that. So, it's a helpful tip. And so that's H, Planck's constant. And then N in the equation, N is the quantum number because energy is quantized. So you can only have things in proportion to N or to 1. Yeah. So, and then frequency is the last aspect of the equation. So based on that, what has higher energy, a red laser or a green laser? Okay, so based on what we know from the electromagnetic spectrum, we can see that, so the shorter, okay, so increasing wavelength goes this way. So we're comparing green to red. So because wavelength goes that way, red has a longer wavelength than green. And as we said earlier, the longer a wavelength, the smaller the frequency. So which would mean red has a smaller frequency than green. And then as we can see in the equation here, energy is directly proportional to frequency. So if red has a lower frequency, that means it has lower energy. And then if green has a higher frequency, it means it has higher energy. So the green laser has higher energy. Okay, the photoelectric effect. Photoelectric effect happens when a light strikes a metal and electrons are emitted. Um, so it depends a lot on the properties of the light. So if it's a low frequency light, then there is no emission. The electrons do not leave the metal. If the light is of or above a threshold frequency, which is V, and then this is subscript, so this is subscript V, yeah. Then the electrons will emit after a certain level frequency, the threshold frequency. If it's increased intensity of light, the number of electrons will increase. So that intensity of light still has to be of or above the threshold frequency, but increased intensity means increased number of electrons emitted. And then if light frequency increases, so like once you're above the threshold frequency, as you keep increasing that frequency of the light hitting the plate, the speed of the electrons emitted will increase. So a way that I like to think of it, this might be confusing, so if it confuses you, like, don't worry about it. But that I like to think of it is like, okay, say that there's people like sitting at some place and you want them to leave that place. So you pay them. And they like they want to stay there. So like you have to pay them a certain amount of money for them to leave. Like if you just pay them 50 cents, they're not gonna leave. They say like you have to pay them $10 and they're like, okay, I'll leave. They pay them $10 and there's like there's like a bunch of people there. You pay one person $10 and that person leaves. If you pay that person like $20, they'll be like, oh, they're paying me a lot. I'll make sure to get out of here. So they'll like leave faster. You pay them $30, they'll be like, oh wow, and they'll leave even faster. Like the more you pay one person, the faster they'll leave. And then the more the more money that you have across people, which would be like the intensity, the more people, like number of people will leave. And then the more money that you pay to each individual person, the faster that they'll leave. So the amount of money towards one specific person is like the frequency, and then the amount of money like for like the breadth of people is the intensity of the light. I don't know if that makes sense. It helps me understand it, but that's one analogy. Um, okay, so light is a particle. Einstein said that light is quantized in light particles called photons. The energy of a photon is frequency. Light is a wave and a particle, and everything has a wave. So Einstein drew off of Planck's research or studies and of how energy is quantized, and he said that light is quantized. And instead of calling it quanta, he called it photons. And we can relate this to a work function. So this tells you, this is related to like the photoelectric effect of the light hitting a metal and the electrons leaving. Because like how I said, like if you pay a person more, they'll like leave faster. So if you give more energy to the metal, the electrons will leave faster, the speed will be faster. And so this equation is calculating that. So it's the Planck's constant times frequency minus a work function, which is Planck's constant times the initial frequency. So this is the amount of energy that it takes to get the electron to leave at all. And then that once you take that away, you have the energy, the kinetic energy, which is how fast the electron can leave. And that is all. So I hope that helped. And yeah, that was lesson lesson 5, section 3.1, 3.5. To review the material. Good luck.